All right, that part's recording. And let me turn this on right here. Start recording. All right, we're recording now. So let me go ahead and pull up uh, let's see, share content, share. Everybody should see the little girl with the kitty cat. And let's see, whiteboard. Here we go. All righty, and let me make sure the meeting stays open before I get started. So lock meeting, unlock meeting. Apparently, if I lock it and unlock it, it'll keep it going. So last time we did lattice energy, and the big thing about lattice energy, which we had the smaller the atom, the higher the lattice energy, the higher the charges, the higher the lattice energy. So it followed that general trend. So let's get into something completely different. And that has to do, first off, let's look at the idea of polarity. Okay, so let's go ahead and get started on that. So, okay, polarity literally means poles. We have poles, okay? And so let's take a look at the classic example, which is hydrogen with fluorine, HF. All right, this is a molecule. We have hydrogen bonded with fluorine. And for a bond to take place, we have electrons in the center. More on that in a little bit, but there's electrons making bonds. Okay, we have electrons in the middle. Let me write that as a little bit better looking E. We have electrons in the middle making bonds. Now, this is a covalent molecule. Covalent means it has shared electrons making bonds. More on that in a little bit. Okay, so if we were to represent these two lines as being a bond and being two electrons, we could draw them like this. And I'm going to try to draw these electrons being more or less dead center between the hydrogen and the fluorine atoms. Okay, now all things being equal, you would think that they would be equally shared between the hydrogen and the fluorine. They are in between, and we would say these are equally shared in an ideal world. Okay, but in fact they're not. Okay, so what ends up happening is that the hydrogen and the fluorine do not share these electrons equally. And in fact, the fluorine really, and I'm trying to exaggerate this, the fluorine really, really, really wants the electrons. Okay. And so the electrons are pulled towards the fluorine. Now, what's the charge on an electron? Electrons are negative. Okay, electrons are negative. And so if electrons are negative, then we're going to, these two electrons here are going to spend more time on the fluorine. And if they spend more time on the fluorine, then this end of the molecule will be slightly more negative. And if the electrons are spending less time on the hydrogen, then this end will be slightly positive on that end, because now you don't see the negative electrons on the hydrogen anymore. You can see more of the proton that's in the middle. So what are protons? Protons are positive, electrons are negative. And so the electrons are more towards the fluorine, so this ends up becomes more negative. Now, it's not an ionic compound. Now, an ionic compound, we have complete transfer of electrons from one atom to another. This is just pulling them over just a little. It's pulling over just a little. So when we say that it's over more on the fluorine, we'll say that this end is what's called a partial negative. And this end over here on the hydrogen, we'll call that a partial positive. Partial being a lowercase delta. This is lowercase delta, Greek letter delta, and a triangle is an uppercase. All right. And when we have a lowercase delta, this means partial. Okay, so there's a partial positive and a partial negative. And if you've had calculus, and you may have done derivatives, you will have seen lowercase deltas, like the derivative of x with respect to y. Well, that means the partial of x with respect to y. Well, it's the same thing here. When we're talking about partial positives, partial negatives, we use a lowercase delta to indicate that. Now, if we were to draw the electron density around these guys, without the electrons moving, we would expect it to be a symmetrical molecule with respect to the electrons. But if we were to draw this in terms of how much the electron density is, in other words, bigger circle means more density, then we'd expect that the electron density would show up as being more on the fluorine. Okay, now, when we have this situation here, we call this a polar bond. That's what we call this. We call this a polar bond. When we have a bond and it's more negative on one end and more positive on the other end, we call this a polar bond. Now, if the molecule itself, this whole thing here, this HF is a whole molecule, we call this a polar molecule. Okay, now these two things are not the same thing. A polar bond and a polar molecule are two different things. They're very much related. Now, we'll do polar molecules in a little bit this morning, but let's talk about polar bonds first off. How can we predict if we have a polar bond? All right. And so a polar bond, the way we can tell, first off, it has a net partial charge. Okay, on each end. By the way, you can't have just a positive end and that's it, or you can't just have just a negative end and that's it. You have to have a plus end, you have to have a minus end. All right, they both go together. Okay, now generally speaking, we have something called a debye, and that tells us the degree. It's a measure of charge separation. Now separation. We are not going to worry about debyes. They're in a textbook. They are a measure of charge separation. Okay. What we're going to worry about is just simply degree of debyes. Now, generally speaking, depending on who you talk to, something less than about 0.3 is considered nonpolar. That number differs depending on who you talk to. It's usually around 0.2, 0.3, point-ish, thereabouts. Less than that is considered not polar. All right. Now, greater than that is considered to be polar. All right, these are just numbers that I'm throwing out here, okay? Like I said, it depends on who you talk to. If you talk to an organic chemist, they'll probably run it around 0.3. If you talk to somebody who deals with spectroscopy, which is the interaction of light with molecules, they may say it's polar around 0.1. It just depends. It's not a hard and fast number. All right, but we're not going to worry about that except to say that it exists. All right, you see what I'm saying? It just exists. Now, from a practical standpoint, because I like to do things from a practical standpoint. All right, and that is, how can you tell? How can you tell? And we'll just, how can you tell? Now, this is, how can you tell? Well, what we do is we look at the periodic table. Basically, if we're left to right separated, it's polar. It's not a perfect rule. It's not a perfect rule, but it works pretty good in most circumstances. If you're talking about like organic molecules, yes, if it's separated left to right, it's more or less polar. All right. And so if we had a series of if we had a series of bonds and we were to look at, say, NH, or let's say CO, well, these guys right here, these carbons are all on the right. And the H right here is far left. But these guys right here, these are separated. These are separated left to right. All right. Now this goes back to the electronegativity, electron affinity, ionization potential. You know, if you saw the numbers differed from left to right. So these guys right here would definitely be, these are all polar bonds. These are polar. These are polar. Both of these are polar. Okay. Now, how about something like this? How about a Br with a Cl? Well, these are up and down. These are up, up, down. And when I say all these, I'm talking about the periodic table. These are up, down. All right. These are up, down. And so bromine and chlorine, while they have a difference in the electronegativity and there is a net charge transfer, these are considered generally nonpolar. It's a nonpolar bond. Okay? And so when we're talking about organic molecules, which is where most of y'all will end up heading at some point maybe, the important ones, polar bonds, will generally be things like NH, OH, FH, and anything involving carbon with oxygen or carbon with some sort of halogen. Okay, those are generally going to be your important polar bonds. They're important because when they show up in molecules, they tend to be very polar and they cause interesting things to happen. Okay, which comes with the charge separation and all that. So if we're going to have important polar bonds, these would be it right here. And a matter of fact, if you look at these guys right here, when you have N paired with a hydrogen, oxygen paired with a hydrogen, or fluorine paired with a hydrogen, these form what are called hydrogen bonds. Okay, and they're particularly important. Okay, and we abbreviate this typically H bond is how we typically abbreviate these. Okay, so we have polar bonds, and about the only essential skill that we have here is, can you tell a polar bond from a non-polar bond? And basically, besides memorizing this very short list of important polar bonds, this very short list, just remember, if it's left to right separated, then it's polar. And if it's top to bottom separated, then it's nonpolar. And of course, if it's the same thing, like N, it's nonpolar. Okay, because that's neither up nor down nor left or right as far as being polar goes. Okay, so here's a very short list. Okay, now More on this in a little bit. Okay, more on this in a little bit. All right, that's kind of an introduction to the whole idea of polar bonds, and what's going to translate into polar molecules later on this morning. Okay, so now the really interesting stuff. Let's do structures. Okay, now structures means the how they're joined together. All right. And this is where it really gets into the real chemistry that goes on. We've talked about reactions, and when we picture chemistry, we picture like mixing some things together and something happens, and if it's really exciting it explodes, right? Because that's really the exciting chemistry, is we can make something explode. And this is true. But what makes these things happen in the first place, a lot of it has to do with structure. A lot of it has to do with how things are shaped. That's how they join together. It's kind of like people, all right? We're basically, if you just look at us in terms of our atoms, we're just a bunch of hydrogen atoms with some oxygen atoms for the most part. We have a little bit of carbon, even less iron. We got some calcium. And if you just take us and put us into a blender and turn us into people mush, all right, all you've got left is just this pile of mush. And that's not very exciting. What makes people do what people do? It's our structure. We have fingers, we have toes, we have eyes and ears. That's kind of like, the kid thing, fingers, eyes, nose, mouth, toes. Well, actually, these are fingers, but, and it's like, that's what makes us interesting. It's the structure, it's the shape of things. So molecules have shapes as well. Molecules have structure. So I'm going to show you how to build a molecule, starting out with just the formula. All right, so first off, our first essential skill here is we have to be able to count valence electrons. Here's our first skill. All right, that's our first skill. So our first thing that we have to be able to do to be able to make structures is to count valence electrons. Now, where are the valence electrons? Valence electrons are on the outside. If you think about it, we're fixing to put together atoms to make molecules, and what's going to be doing the joining? The joining is going to be the things on the outside, because they have to bump up against each other to be able to make bonds, to be able to join up together. So it's the stuff on the outside that matters, kind of like people. It's not the inside really, it's the outside. Okay. And so, same thing with atoms. All they really care about each other is what's on the outside. All right. And that outside is called a valence electron. Now, how do we find the valence electrons? Well, if we look at the periodic table, and I'm going to draw a very crude one here. If we look on the periodic table like this, and hydrogen being right there, okay? And here are your transition elements in the middle. We can count the number of valence electrons, and it goes 1, 2, 3, 4, 5, 6, 7, 8. And here are your noble gases, just to give you an idea of the layout. Everybody see how that runs? So, and it's also the same as the group number. In here, in the middle, we won't care about those. Where those transition elements are, we won't care about those. Just keep in mind that if we do have metals in there, they generally, for our purposes, will be for ionic compounds only. Okay. And we're not interested in ionic compounds. We're interested in covalent compounds which share electrons. That's where all the interesting, exciting stuff happens, is with covalent compounds. So the first thing we need to be able to do is count the valence electrons. And I will mark in red here because we do not want to be this person, right? That's what red means. Not total electrons. All right. So when we say there are 7 valence electrons, for instance, we mean it's 7 all the way down. When we say there's 4 valence electrons, we mean it's 4 all the way down. All right. So for instance, chlorine has 7 valence electrons, right? Chlorine equals 7 valence electrons. Not, what's chlorine? 17. Not 17. Okay? 17 is a grand total for chlorine. All right, 17 is total for for chlorine. It has 7 valence electrons. These are the outermost electrons. Common, and I'll put it right here in my rainbow color, common amateur mistake. Common mistake. Common mistake is to start counting up valence electrons and start going with grand totals. It's not the grand total. We only care about the outside. All right. So if you look at 7A, which is also group 17, as you go across, you see the halogens would be fluorine, chlorine, bromine, iodine. Fluorine, chlorine, bromine, iodine. All of them have 7. All of them have 7. Those are your outermost. What's your core electrons? Those are the previous completed shells. Like for chlorine, the previous completed shell would be neon with 10 electrons, okay? All right, so our first skill here is count your valence electrons. All right, that's my first skill. All right, now let's make a molecule. Let's start with the simplest one that I can think of, which is, and I'm going to switch colors here. We're going to start with CF4. Now, what's the name for CF4? CF4 is carbon tetrafluoride. So I'm just going to write out the name here. So how do we name this? First off, this is a covalent molecule. This is covalent. How do I know it's covalent? It is a non-metal with non-metals. Okay, that's how I know it's covalent. It's a non-metal with a non-metal. Carbon is in our non-metals, fluorine's in our non-metals, okay? So I know it's covalent. Covalent also means shared electrons, okay? So we're sharing, all right? Now, what is the name? How do we name this? We name what it is, and we name how many we have of each one. So carbon, there's just one, so we say carbon. How many fluorines are there? 4. 4 means tetra. Tetra means 4. And so we say tetra fluor. Since there's just the atom, we say ide, so we say fluoride. Carbon tetrafluoride. Okay, so these are all skills. Look, aren't these skills from previous chapters? They sure are. That's the beauty of a real science, like chemistry, as opposed to like sociology. It's a real science. And so it builds on everything prior. Okay, so we have carbon tetrafluoride. All right, step 1. We are going to count the valence electrons. All right. So how many valence electrons do we have? Well, what we do is we just work our way left to right. And I say carbon. First off, we say carbon. How many carbons do we have? I have 1. How many valence electrons does carbon have? We count across the periodic table. We look at our periodic table and we go 1, 2, 3, 4. 1, 2, 3, 4. Carbon has 4 valence electrons. And we say 1 times 4, well, that's exciting. That gives me 4 electrons. Now remember, it's not the same as total, it's just valence. And then we look at fluorine, and we say there are 4 fluorines. So we say 4 fluorines times, and we look on our periodic table, and we look across, and we go 1, 2, 3, 4, 5, 6, 7. Fluorine is in the 7th group. Looking across, and we say 4 times 7. What's 4 times 7? It's 28. All right, one of the skills that you have to have here is be able to multiply numbers. And you also have to be able to count. See, there's 4 on the F. This is an important thing up here. I want to mention that as an aside here. You know, I like to show things easy to mess up. Easy to ignore. All right, what do I mean by easy ignore? You just kind of go with it, okay? If it says that there's a 4 there, then that means there's 4. It sounds like a silly statement to make, but I can tell you how many times I've seen folks who will put down a 3, or they'll put down a 2, or they won't even put down any number at all. They'll just say there's 7. Well, there's 4 of them. So 4 times 7 is 28. Now, next thing we do is we add them up. What's 4 plus 28? It's 32. Total. Okay, so we have counted up the valence electrons for carbon tetrafluoride, and it has 32 electrons. Total valence electrons. As a matter of fact, I'm just going to go ahead and just put down valence electrons right here. There you go. It has 40, 32. It has 32 valence electrons. Okay, now, what are we going to do with these things? All right, let me slide this up here. I'm going to slide. Hopefully everybody can see this just like I can. All right, now, step 2. Atom that's alone. Go center. Arrange the rest around. Okay, so what's the atom by itself? What's all by its lonesome? The carbon. There's 1 carbon. Now, I want to point this out though. The carbon over here happens to be on the left-hand side by itself. That does not mean a thing. Okay? Whatever is by itself goes in the center. It is not necessarily the left-hand side atom. Think about H2O. What's by itself? The oxygen. But it's on the right-hand side. You see that? The oxygen would go in the center in that case. Just because it's on the left-hand side does not mean anything. That's what I mean by that. Okay, so if it's in the center, if it's by itself, it goes in the center. So let's do that. Let's go ahead and put it in the center. So we say carbon goes in the center. And we're going to arrange everything else around it. Now, look, I like to go north, east, south, west. In other words, points on the compass. So I'm going to say north, east, south, west. And we're going to say here, note, there are 4 fluorines. Okay, look what's up here, 4. All right. I emphasize this because if I don't mention this, I will have people put down 3 fluorines, 2 fluorines, just 1 fluorine. That it's come on. How many fluorines do you have up there? You have 4. All right, 4 have to make it down here. So we have 4 fluorines. There we go. I'm moving this up. Okay. Now, step 3, we're going to make a bond for each atom. And that is 2 electrons. Okay, we're going to make a bond for each one. Now, what's a bond look like? It's 2 atoms. I mean, it's 2 electrons. So here's a bond. There's a bond right there. You see that? There's 2 electrons. That's a bond. Otherwise known as a bonding pair. All right, and then we're going to put 2 here, 2 here, and 2 here. All right. And we're going to subtract off of total. All right, now what's the total? Well, the total we started out with was 32 electrons, okay? So we have 32 electrons over here. I'm going to start in black. Okay, so we have 32 electrons total, which I just copied down here. Now, how many electrons did we just put down? I just put down 2, 4, 6, 8 electrons. So I put down 8. So we're going to subtract off 8. Okay. We're going to subtract off 8. And 8 from 32 is 24. Okay. We're doing a running total. Now, here's your second skill. Your first skill is to be able to add. Your second skill is to be able to subtract. Okay, so we have to be able to subtract off 8, and we have to go to 24. Now, step 4. Add remaining electrons to outside up to, up to 8. Okay, up to 8. Except I can't spell this morning. Yeah, there it is. Except hydrogen, which is happy with 8, 2, sorry, happy with 2. Boron, well, I wrote it right, which is happy with 6. Okay. We want to put up to 8 on the outside, except for hydrogen, which will be happy with 2, and boron, which will be happy with 6. Okay. Now look. All right. So we're going to do that up here. We'll change colors here. We'll change to green. All right. Now, when I say up to 8, I include those blue electrons I put up there. I'm including those as the shared electrons, but they're sharing on everyone. So they're not just on the carbon, they're not just on the fluorine, they're on both at the same time. And so I'm going to say 1, 2, 3, 4, 5, 6. But there's 2 more over here, and that makes 8 total. Y'all see that? It's 8 total there. Okay, now I have 4 fluorines, so I need maximum of 4 times 6, which equals 24. Because there's 4 fluorines, and I have room for 6. I have room for 6. Okay, I got room for 6 on each one. And there's 4 of them. So 4 times 6 is 24. Do I have 24? I do. So I say, yes, I have 24. And so I have room for 24. So I'm going to subtract off 24. And I'm going to go ahead and put 6 on each one. There's 2, 4, 6, 2, 4, 6, 2, 4, 6. And there we go, all the way around. Okay, and I put down 24 electrons, and I subtracted off 24, so I have 0 left over. Now, it is very important that we do not add any more than what you have in electrons. It's also important that we use up all the electrons, so we should always have 0 left over at the end, no matter what we do. All right, so don't just add electrons in there because it doesn't look right, okay? Just make sure. All right, so now the last step that we need to do is we need to check for octets. Octets. Or happy atoms. Really what we're looking for is happy atoms, not so much octets. Remember the octet rule? The octet rule is atoms gain, lose, or share electrons to have a full valence shell. They don't necessarily have 8. But let's go ahead and check and see. So let's check and see. Let me change colors here. I'm going to do red just because it's the one that's left. And we look here. How about these fluorines? They have 8. And all 4 fluorines are the same. You see that? They all have 8 electrons around the fluorine. How about the carbon? Well, the carbon, that's easier to see because it has the blue. But look at that. Now I'm just circling this to draw your eye to it. This is not something that you do on paper. Generally, I can't show you my finger. All right. But I can show you with my pen. Okay, so generally you circle with your finger and you count and make sure you have 8 electrons. So sure enough, everybody's happy here. Yay. So this is the structure, and if we were to write this out, a lot of times what we'll do is we will replace bonded pairs. See that bonded pair up here? A lot of times we'll replace these bonded pairs, we'll replace them with lines. And so we'd say carbon with a line going to the fluorine. To be complete, we would still put in those non-bonding pairs. This is a non-bonding. We'd still put them in there, but we would replace the bond with a line. Here we go. There we go. So we have replaced the bonding with lines, and that's our structure right there. Okay. So what have we done here? So the first thing we did was we counted up our valence electrons. We got a total. Then we took the atom that's by itself, the element by itself, and we put that in the center, and we made one bond. We subtracted off all the electrons that we used to make that bond. Then we went to the outside and whatever electrons we had left up to 8, or 2 with hydrogen and 6 with boron, up to a maximum, we added on there and then we subtracted them off. Now, in this case, we didn't have any left over. All right, so let's do another one. All right, so we're gonna do this now. So let's do what should we do here? How about let's continue with carbon, except this time we're gonna do CH4, otherwise known as methane. Methane is its common name. CH4 is methane. It's the simplest organic molecule. All right, we have methane, we have CH4. Now we want to draw the Lewis dot structure, which is what this is. We want to draw out its structure. All right, so what's step one? We're going to count the valence electrons. So we go carbon, hydrogen. We say there's 1 carbon, so there's 1 times 4, which equals 4 valence electrons. And the hydrogen, well, there's 4 of them, and they're 1 apiece, so that gives me 4 there, and that gives me 8 total. 8 valence electrons for the whole molecule. Okay. So carbon is the one by itself, so we're going to put carbon in the middle. We're going to put hydrogen all the way around. North, east, south, west. We're going to make a bond. What's a bond? A bond is 2 electrons. So we make, here's a bond. We're going to glue them on in a sense, because this is what's holding them on. There we go. We made 2 electrons per bond. We glued on each hydrogen. There's 4 of them. How many electrons did we just put down? We put down 8. We have none left. So now we go through and we check and make sure everybody's happy. Now the carbon, is the carbon happy? And the answer is yes, the carbon is happy. How about those hydrogens? Well, hydrogen has 2 on it, but remember the rules. Hydrogen is happy with 2. Boron, happy with 6, and everybody else wants 8. So this molecule is happy. So this is one happy molecule. There you go. All right, now, and if we were to draw this with lines, it would look like this. We replace the bonds with lines, and any extra electrons we put as non-bonding pairs. Okay, so far so good, huh? Not so bad, not so bad. All right, let's do another one. How about this guy right here? I like using fluorines. Nitrogen trifluoride. How do we name these things? First off, this is everything we're doing is covalent, but this is a covalent compound. How do you name this if it doesn't have a common name? You would say nitrogen. There are 3 fluorines, so we'd say trifluoride. There we go. Nitrogen trifluoride. All right, so what's the procedure here? And you may say to yourself, I've got this, Mr. Pierce, I've got this. Okay, but look, here's nitrogen. There's fluorine. Let's see, nitrogen, we look on our periodic table and we count across and we go 1, 2, 3, 4, 5. We see 5 for nitrogen. We're counting up valence electrons. Remember, it's not the same as a total. And we see fluorine. Now, how many fluorines do we have? We have 3. See what I mean? If you're in a hurry, if you're not paying attention, you might put down 4. But it is 3 fluorines. Fluorine is 1, 2, 3, 4, 5, 6, 7. 7 valence electrons, which is 21. Grand total is 26. 26 electrons. All right. Now, nitrogen is by itself, so let's go ahead and put nitrogen in here. And then we say nitrogen, fluorine, fluorine, fluorine. Now look, there's 3 fluorines over here. Better be 3 Fs over here. All right. I know it seems silly. I know y'all probably say, oh, but of course, Mr. Pierce, it's 3. I can't tell you how many times I've seen people do this. They get so used to seeing 4 that they want to put 4 down every time. If there's only 3, there's only 3. If there's only 2, there's only 2. If there's only 1, there's only 1. Okay. All right. So I see 3 fluorines up there. Let's make a bond. Bond is 2 electrons. There's 1 bond. There's 2 bonds. There's 3 bonds. 3 times. How many did I put down? Put down 6, right? Minus 6 gives me 20. By the way, ladies, guys, don't skip steps. It's kind of like when I said chapter 3, I was doing molecules and ions, we're putting them together. And I said, don't skip steps because you will regret it. You skip steps here, you will regret it. All right, so now what? How much room do we have on each fluorine? How much room do we have? We have room for 6, right? Room for 6 on each one because we go up to a maximum of 8, except for hydrogen was happy with 2 and boron, which is happy with 6, right? We have room for 6. There's 3 of them, so 6 times 3 is 18. Do we have 18? At least. And the answer is yes. Okay, so we subtract off 18 because we have room for 18. That will leave me with 2. So let's go ahead and put those 18 up here. 2, 4, 6, 2, 4, 6, 2, 4, 6. I subtracted off 18. I have 2 left over. Here they are. Now, everything we've done so far, we had nothing left over, right? We had nothing left over. Now, what am I going to do with these 2? Well, so what did we do? We went inside. We went inside to make our bonds, right? Then we went outside to put the electrons down. Now we're going to go back inside as a lone pairs. So any extras you have go back in as lone pairs. And so they're going to go back in right over here, back to the inside. So we went inside, outside, back to the inside. So this is now a lone pair. That is called a lone pair. It's a pair of electrons and it's all by its lonesome. All right, that's called a lone pair. Now, what I like for y'all to do to emphasize that they exist and that they take up space is we're going to circle these guys. We're going to circle them, the lone pair. Now, I do that for two reasons. The reason why I circle lone pairs is first off, it's my habit. Like I said, sometimes it depends on where you learned chemistry and what part of the country and what part of the world. And my part of the world says circle lone pairs. Okay. Also, the reason why you circle lone pairs is they take up space. More on that with geometries. When we're looking at geometries, it's important that we understand that lone pairs take up space and that they exist. Okay. Sometimes we forget that electrons take up just as much space as atoms do if they're just floating around. All right, now let's check for octets. Let's check for happy atoms. Okay, so we're going to check for happy atoms now. So let me check these fluorines. Now these fluorines are the same all the way around, so it's only important that we check one of them. So I'm looking around here and I checked that fluorine. And what do we know about that fluorine? It does have 8 electrons. We got the 3 times 2, 6 red ones plus the 2 green ones. That's 8. Fluorine is happy all the way around. How about this nitrogen? How about this nitrogen here? Let's take a look around this nitrogen here. And it doesn't matter whether it's a bonding electron or not. It's on the nitrogen. It's there. It's on there. How many electrons, how many dots do you see on that nitrogen? I see 8. I see 8. And so the nitrogen, sure enough, the nitrogen is happy as, well, there it is. The nitrogen is happy. And so the whole thing is happy. So yay, hooray, it is happy. So if we were to sketch this out with lines, we would say like this. We would go N, fluorine, 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 and we would still have that lone pair circle. I like to put them up on the high end. And then we would have, of course, the 6 dots on each one. There we go. Nitrogen trifluoride ends up with a lone pair. So extras, if you have any extras, they go as lone pairs. That's what you do with them. They go as lone pairs, okay? That's where they belong. All right, let's do another one. I just love doing these because there's a procedure. Do you see the procedure? Do you see there is a method to this? And this is where it becomes important that we don't skip anything. If you start skipping, bad things will happen. All right, let's do another one. All right, now, sometimes we're going to have a situation where we have to do something with them other than just add electrons. Let me make sure I'm the right color here. Let's do carbon dioxide. There's the carbon all by itself. We have 2 oxygens, so it's di. It's an oxygen, so that ox. Since there's 1, it's an odd. Carbon dioxide. Naming does not go away. All right, that's carbon dioxide. So let's follow the same procedure. I'm going to show y'all there's something different going on here, though. All right, so we have carbon has what? 4 valence electrons. Oxygen, there's 2 of them at, what is it, 6 apiece, right? So we count across, we go 1, 2, 3, 4, 5, 6. Remember, we got to count all the way across, so that's times 2 is 6. That gives me 12. And I add these guys up, that gives me 16 total. All right, now carbon, it's 1 by itself, so it goes in the center. And I'm going to go ahead and just put the oxygens off to the side because I already know what the structure should be. So I'm just going to go ahead and set them off to the side like that. Now, what's our next step? We have the carbon in the middle. We have the other atoms are surrounding it. So what's our next step here? Our next step is to what? Make bonds, right? So let's go ahead and make some bonds. So I'll make one bond, make two bonds. Here's my second bond. I've only got two things to glue on, so I'm only making two bonds, right? There's two oxygens in the formula. There's two oxygens in the molecule. So there's only two, and I made two. How many did I use up? I used four. So I said minus 4 gives me 12. All right, so that gives me 12 left over. If I've added them up right, have I added them up right? Okay, I'm good so far, right? Adding and subtracting is a skill here. So now, how much room do I have left? How much room? Well, there's room for 6 on each one, and there's 6 times 2 equals 12 electrons. That's how much we have room for, right? And that's fortunate because I have 12 electrons over here. So I go minus 12. I have that much room. And so let's go ahead and put those 6 electrons on. So we go 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Now remember, we did the inside. We're going to the outside. All right. We've run out of electrons. Now remember what I said before. Don't put down any more electrons than you have. You don't want to have any left over, but you don't want to put down more than what you have. So I don't have any electrons left over. Let's check for octets. So let's check. So we go, how about those oxygens? How about those oxygens? Hey, they're happy, right? Oxygen's happy. How about that carbon? Whoa, wait a minute now. How many do we have here? We have 4. Carbon is not happy. Not happy. Okay, so what are we going to do? Look, I cannot emphasize this enough. Don't just start putting down electrons. You can't do that. We're out of electrons. There's no electrons to put down. So what can we do? Well, what we can do is we can take a non-bonding and we can shift. We're going to shift in to bonding. Okay, we're going to shift into bonding. So this pair right here is going to shift in. So I'm going to draw it a second time just to show what's going on here. I just shifted those guys in. All right. And what I'm doing is just reproducing what I had to begin, but now I shifted in these electrons. Ah, come on, blue. There it goes. There it is. All I did was just shift in. I didn't move them. Now, this is important. And this is something when I was in your position, it wasn't explained to me properly. Those 2 electrons that just shifted in up here never left the oxygen. I didn't move them off the oxygen. What I did was I shifted them so they went from non-bonding to bonding. They went from not being shared to being shared, but at no point did they leave. And also, this was never properly explained to me, they never stopped being a pair. In other words, you don't take them off as a pair and go, okay, I'm gonna put one over here, one over there. You don't do that, okay? Just don't do that. All right, so they shifted over. Now let's check again. Is it happy? So is carbon happy? Now I haven't done anything to the oxygens if you think about it. Since the pair never left the oxygen, it's still on the oxygen, so the oxygen still has 8. However, the carbon now has 6, so carbon's still not happy, still not happy. Still not happy. Okay, still not happy. So now what? Well, what we can do is we can go ahead and we can move um, or shift. Since nature really likes things to be symmetric, let's shift from the other side. And by the way, it doesn't matter which pair I shift. Let's go ahead and shift these two. I'm going to shift these two in. I could pick any pair you want, but since I did the right, I'm going to do the left. And out of those three choices over here, of those blue pairs on the left-hand side, I could have picked either one of the three. It doesn't matter. And if I shift now what does it look like? Well, I didn't do anything over here, so it's still got the 2 in the middle. Now I shifted those 2 in, and so now I have 2 pair in the middle, and I have those 2 that are left over here. All I did was shift it on in like that. See? That's all I did was shift it in. Now is the carbon happy? And we look, and when we say happy, I mean everybody in here counts. Now, just because these 2 right here look like they're on the oxygen, they're not. It's a graphical representation. If they're in between, they are shared equally. I just got to put them somewhere, so I put them side by side. It's just a graphical representation. I'm not trying to say literally one pair is on the carbon, one pair is on the oxygen. They're both shared equally. So now the carbon is happy. The oxygens are happy. Okay, and now if we draw this, we're going to draw it like this. We're going to say carbon double bonded to the oxygen, carbon double bonded to the other oxygen. We're going to have those 2 non-bonding pairs on each oxygen. Do you see that? And so now the carbon's happy. Remember, each line represents 2 electrons. Each line represents a bond. And so we got, each line represents 2 electrons. So we got 2, 4, 6, 8 on the carbon. We have 2, 4, 6, 8 on each oxygen. It's happy. By the way, this right here, these guys, guess what it's called? When you have 2 lines together and you have 2 bonding pairs, guess what this is called? This is called a double bond. And guess how much stronger a double bond is than a single bond? Twice as strong. It's one of the rare things that makes sense. Okay, I've gone a little bit over today before break, so I'm going to go ahead and turn off the recorder. Stop. There it goes. I'm